Chapter 5, Topic 5.1 and 5.2, 2D equilibrium of a rigid body. So before we, so that let's first talk about what's the difference between a rigid body and a particle. So whenever in statics, engineering mechanics, and dynamics both, whenever we talk about solving problem, we either consider an object as particle or a rigid body. So when we consider something as a particle, that means it has only mass, and we do not consider shape and size of the object. So even an object can be as big as an aeroplane or a train or a cruise ship. We can still consider that as a particle because the motion along which this object moves is much larger than the size of the particle. So whenever we consider anything as a particle, all we care is about the mass. Now, rigid body on the other hand, whenever we consider an object has a rigid body, we include the mass of the object, its shape and size. So this is what we consider for rigid body. So this chapter is about rigid body and how to calculate the support reactions for the rigid body. Now, before we talk about any supports and reactions, let's talk about the concept called degrees of freedom. So let's consider that this is our rigid body in two dimension in xy plane only, where x-axis is horizontal, y-axis is vertical. Now when this object is free completely from all the surroundings, then it can move along x direction in linear direction, it can move along y, or it can actually rotate about an axis perpendicular to xy plane. So these three, 1, 2, and 3 are called 3 degrees of freedom of two-dimension object. So an object in two-dimension plane has 3 degrees of freedom. On the other hand, let's consider this object which is in 3-dimension world where x-axis is here, y is here, and z is here. And this object, again, when it's completely free from its surrounding, the object can translate along x direction, it can translate along y direction, it can move linearly or translate along z direction. Other than that, it can rotate about x-axis, it can also rotate about y-axis, and it can rotate about z-axis. So this object has 6 degrees of freedom, out of which 3 degrees of freedom are translation and other 3 degrees of freedom are rotational. So this is the concept of degrees of freedom. But whenever an object or a system is built in real life, an object is not isolated from all of its surrounding, but it's always supported, or it's always connected to other objects by means of joints. So whenever we introduce supports and joints into physical systems, then we restrict the degrees of freedom. For example, in this two-dimension plane, if we add, let's say, a pin at the center of this object, and that pin is rigidly connected, that pin is connected with the background, then this object cannot translate along x direction, it cannot translate along y direction, all it can do is this rotation. So we have restricted 2 degrees of freedom. That means this particular pin support has 2 constraints. And whenever we restrict the degrees of freedom, that means we are introducing constraints. So there are 2 constraints, no translation in x, no translation in y. Same way, in 3-dimension object, at most we can have up to 6 constraints. And when object is introduced 6 constraints in 3-dimension space, that means we are restricting all of the degrees of freedom, and then object cannot move at all. Okay. So this is the concept of degrees of freedom and constraints, and based on that we can now define different types of joints or supports. We have, until now, we have not considered this joints and support. For example, this is the problem from chapter 4, where we calculated the equivalent point load. But let's see, where are the supports here? So this beam is not completely isolated, it's not completely free from its surrounding in xy plane, but it's being supported at A and at B. So these are called supports. And this supports they restrict degrees of freedom, and thereby there are support reactions whenever they restrict the degrees of freedom. For example, this type of support here is called roller support. So this roller support allows the beam to translate in X plane, but it does not allow translation in Y plane. So there is a support reaction coming from this support, which prevents the translation along Y direction, and this support reaction is called BY. B because this point is B, and Y means it's in vertical direction. On the other hand, this type of support is called pin support. Now, whenever a pin support is being introduced, it prevents the translation along horizontal direction as well as along vertical direction. So there are two support reactions, AX and AY. However, this freely allows the rotation about pin. So there is no restriction or there is no constraint about rotation of the beam with respect to A. It can freely rotate, but it cannot move in X and Y direction. So there are two support reactions. So in chapter 5, we are going to study how to calculate these support reactions. Let's look at this forklift and the pipes example. So the pipe is being supported on the forklift. So this is the actual photo of that assembly. But what we have seen here, this is called idealized model or idealized diagram. So idealized diagram is just simplified diagram for the real, like the physical system. And we can see that this pipe assembly is being supported at the fork at 1 point, 2 point, and this another pipe is being supported by the first pipe and at this point. So wherever these supports are there, there are support reactions. So there is one support reaction here, there is another support reaction here, there is third support reaction here, and there is fourth support reaction between these two. Other than that, this pipe is a rigid body, so it has weight and shape and size, and the weight of the pipe acts through the center of gravity. So this is the weight of pipe 1 and this is weight of pipe 2. So this is called our free body diagram. So in idealized model or in idealized diagram, we just draw the diagram. We don't add like any of these force arrows, but in free body diagram, we do add them. There's another assembly for the ramp of the truck. So this ramp is being supported by a cable. So there is this cable here, as well as it's being supported by the pin. So there is pin and cable are two important parts of the system that supports this entire ramp on the body of the truck. So this is the real photo, and here is the idealized model for that, or idealized diagram. G indicates the center of gravity or center of mass for this beam. So whatever is the weight of this, ramp, so whatever is the weight of the ramp, W, that acts vertically downward through center of gravity. And now there are two support reactions here, like there is cable tension T in the cable supports this beam, as well as this pin has the vertical and horizontal support reactions AX and AY. This pin freely allows the rotation of the ramp about the pin itself. However, it does not allow the translation motion of the beam. So there are two support reactions coming from this pin as well as support reactions for the cable from that pin. On the other hand, look at this beam. That beam is rigidly fixed to the wall here. So it restricts all the degrees of freedom of this beam in two-dimension world. So the support reactions are AX, AY, but the beam cannot even rotate because it's rigidly fixed. So there is also couple moment M acting at A. So MA. So these are three support reactions for this rigid support: horizontal and vertical translation forces and rotation about A. Let's look at one more, few more examples. So this is the brake assembly for the tractor, and this is the actual photo, and this is simplified diagram, and just identify different supports here. So this is pin support. This is also like this is fixed support, and this is also fixed support. So at all these points there are support reactions. For this platform that is being supported on the tower, it's being supported at pins as well as it's being supported by the cable. Now this platform has some weight W which acts in the downward direction. So these are the different types of supports. And this is idealized model for that platform assembly where A is a pin support. So there are support reactions are AX, AY, and at B there is tension T. And this is W which acts in the downward direction. It's a three-dimension example where the slab or this platform is being supported at A, B, and C hooks. So there are support reactions coming from A, B, and C, and there are tension forces in these three cables. It's another 3D example for the pipe assembly where it's being supported by bearings. So it's bearing B, bearing C, and bearing A are three different supports. So for this part of the video, we just focus on identifying the supports, different types of supports. So now we can go back and look at the presentation. Equilibrium of a rigid body and free body diagram. Identify support reactions and draw a free body diagram. If a support prevents translation of a body, then the support exerts force on the body. Internal forces are never shown on the free body diagram of a whole body. So whenever we draw an object such as a beam, we do not show the forces within the beam, inside the beam. These are called internal forces. And the reason we don't do them is internal forces have equal magnitude but the opposite direction. So they don't play much role for overall external analysis. However, they are very important when we talk about the strength of the component. So we have seen this example. So truck assembly, the ramp has weight of 400 pounds each. So there are two ramps. Each ramp is pinned to the body of the truck and held in the position by a cable. How can we determine the tension in the cable and the support reactions? So when we draw this idealized model, and this is free body diagram, we can see that number of unknowns are 1, 2, and 3. We know weight of the truck, but we do not know other three unknowns. So there are three unknowns. That means technically we need three equations to solve for three unknowns. And those three equations for two-dimension object are called equations of equilibrium. We can call them EOE, equations of equilibrium. And those equations are sum of forces in x direction equal to 0. Now let's define what is an equilibrium. So an equilibrium is when an object, it's in equilibrium from surrounding, means it's not in motion, it's completely stable. For example, right now this ramp is stable, it's not moving up or down. So that's called equilibrium. So when it's in equilibrium, that means the net force and net moment acting on that body is 0. That's why it's in equilibrium. So sum of forces in x equal to 0, sum of forces in y equal to 0, and sum of moments about a point is 0. So there are three equations, and using these three equations, we can solve for three unknowns. So how are the idealized model and free body diagram are used to do this? So yes, we draw the idealized model and free body diagram, indicate the forces, define the coordinate system, and apply three equations of equilibrium. Now, the pipe assembly, the same thing. We have number of unknowns are 1, 2, and 3. We already know the weights of those two pipes, so we can solve for three unknowns using three equations of equilibrium by first drawing idealized model and then later drawing a free body diagram. Okay, so when a particle is in equilibrium, sum of forces equal to 0 and sum of moments equal to 0. So no translation, no rotation. That means no degrees of freedom at all. Okay. First, we draw an idealized model because that helps us to simplify the actual real structure by a diagram, and then later we add the forces and complete the free body diagram. When we indicate forces, we show both the active forces and support reactions. They are called reactive forces. For example, weight is the active force, but tension T is the active force. AX and AY are support reactions. Finally, we need to apply the equations of equilibrium to solve for any unknowns. Okay. So once again, that fixed beam example. So equations, support reactions are AX, AY, and MA. So we have three unknowns, and we can solve for some three equations of equilibrium. Now, different types of supports that we have seen. So if it's a pin support or smooth pin or hinge support, then there are two support reactions, Fx and Fy. Means this support does not allow translation along horizontal and vertical directions. So there are reaction forces, and those are called support reactions. Whenever it's a fixed support, it prevents translation along X, along Y, and rotation about that beam. Because it's a fixed support, it does not even allow rotation, while the pin support allows this rotation. So this is permitted. But here that's not permitted, so this is not allowed. Okay, so there is third support reaction here. When it's a roller support, then that's the support reaction. Okay, so yeah, you can read this as a general rule. If support prevents translation, then it adds a force which prevents the translation, acts in the opposite direction. Similarly, if rotation is being prevented, for example, this fixed support, couple moment is exerted on the body in the opposite direction.